Yes, you are welcome. This afternoon, today we are going to explain everything that happens within capacitor. This capacitor is two parallel plates that sandwich a dielectric that is used for storing charges. That is the main function of a capacitor. So, in most cases, what happens is that there must be a source of the EMF to drive those electrons, and we know that once electrons are flowing, electricity is generated. So in the course of the generation of this flow, charges are being stored in the capacitor. So we are going to look at a simple circuit. Let us take this as a voltage source, this as a key, this is a resistor, and a capacitor there. So if you take this as our V voltage source, you realize that this is our resistor and this is our capacitor. This is the key for switching. So what happens is that a current is meant to flow in this circuit. Because this resistor and the capacitor are arranged in series, what will happen is that as the current is flowing, the charges begin to store themselves at these two plates. This is the capacitor. This is just the symbol. If you go to the lab, it will show you the sample of what we mean by capacitor. So we are taking a sample of this, and we are going to, from here, move you to getting those equations that you can use to determine the amount of charge here as a function of time. So if we are going to take the algebraic sum of all the voltages in this system, we will realize that it will be the voltage source is equal to the voltage across the resistor plus the voltage across the capacitor. Okay? So from here, we can see that voltage source minus the voltage across the capacitor will give us voltage drop across the resistor. Okay, if we agree up to this point, I want you to realize something. The voltage across the resistor normally, according to Ohm's law, is given by I R. This is the current. And if you recall our general knowledge about the capacitor, we say that the capacitance or the charge is equal to the product of the capacitance and the voltage. So, or the potential difference across the points. So, if this is true, we realize that if we take the derivative of these two quantities, it will be, because the capacitor is going to be constant, the one that will be changing is this. So with time, they will be changing with time. So you see, if you agree with this, that when you are changing, there's a change in the charges as with respect to time, the voltage is also changing as well. And then you recall that I, from the general knowledge, is the rate of change of charges, that is the QDT. Therefore, we can substitute for this I in this equation to give Vs minus Vc equal to, let's take this as I, C dV voltage across the capacitor dt multiplied by the resistor. because V is equal to IR. So I is this multiplied by that. Now, we can now see that this thing has become beautiful because it has now become a differential equation. And for us to solve the differential equation, I want you to pay attention. Solving this differential equation will enable us to get almost all the functions we need. We are taking you can write this as this Vs minus Vc is equal to Rc. Let the current, the resistor come for the Vc dt. The Vc dt. So now, it is easier for you to see here that from here we can divide both sides by Rc. If we do that, Rc, this will vanish. So what we for survive is Vs minus Vc all over Rc equal to the Vc dt. Now, the whole of this is still intact. What do we need to do here? Let us factorize. If you factorize negative 1 over Rc, it will be equal to Vc minus Vs. Okay? And this is still going to give you the Vc dt. So now we do what we call separation of variable. If you separate the variable, what we will have is this. We will have this. If we separate the variables, you know that this can come up. So you have minus dt all over Rc. Taking this to the other side is equal to the Vc is already here, so this will come down, which is Vc minus Vs. Okay, so from here, now we have separated the variables. What do? We integrate both sides. So if we integrate both sides, this will give me minus 1 over Rc integral dt. It's equal to integral 1 over Vc minus Vs dVc. Okay? But we know we are not dealing with an indefinite integral, so there must be a limit of integral. So if we take the limit from here, 0 to t, because once you turn the switch on, the current will start building. So there was a time we were not taking record, so that is 0. And the same thing happens here to a certain charge Q. So with this, what we do is to simplify further. And that will give me, if we do this integration, integral of the t is something as t. So we have minus t all over Rc is equal to, this integral will give me ln Vc minus Vs minus ln into negative Vs. Negative Vs. I have taken the limit, so that is upper minus lower. So, and that leads us to having negative t all over Rc equal to ln Vc minus Vs minus ln negative Vs. That's what we have here. And then I need you to recall your laws of logarithm. And because this is natural logarithm, the law still holds. So when you are taking the difference of two logarithms, what happens? You take the quotient. You take the what? The quotient and to subtract the dividend from the, you subtract the divisor from the dividend. And that will give me negative t all over Rc. If I see the word, is equal to ln this minus this, which is Vc minus Vs all over negative Vs. So at this juncture, we can take the exponential of both sides. If you take exponents of both sides, taking exponents of both sides will give me, if I take exponent of both sides, what I have is exponential negative t all over rc is equal to exponentially vc minus vs all over negative vs. So what happens if you take exponent is that exponent cancels the natural log, and so we have exponential negative t all over rc is equal to vc minus vs all over negative vs. So now it's looking pretty. So what do we do? From here, we cross multiply. So if we cross multiply, the essence is to make vc the subject. We'll have negative vs e negative t all over rc is equal to vc minus vs. So what do? You add vs to both sides. If you add vs to both sides, the vs in this side will collapse. So you have vs minus vs e raised to power negative t over rc and equal to vc. So if we can rewrite this as vs by factorizing into 1 minus e negative t all over rc, this equation is beautiful. Now, there's what we call the time or tau. That tau is rc. The symbol is tau. For those of you who care to know, this tau is the same thing as saying rc. What is tau? Tau simply means exponential. That is 1 all over exponential, and that is the time it takes for this charge to get to 37%. To charge up to 37% until it's a constant. So if we put this tau into the equation, we have vc equal to vs 1 minus exponential minus t all over tau. This is the equation to determine the voltage and the capacitor when the time is mentioned. Once you mention the time, this equation will do the justice for that problem. Thank you. Yeah, now that we have come back for a short break, you see we have achieved something by getting the instantaneous voltage across the capacitor at any instant in time. So now let us go back to the circuit we've drawn before and redraw that circuit so that we can get other items from the circuit. This is what we do: the voltage source, this is the key connected to a resistor and then to a capacitor. So this is the resistor, this is the capacitor. Now we have gotten the voltage across this capacitor at any instant in time. How do we get the voltage across the resistor? So let us recall from this voltage source. Recall that voltage source is the same thing as the voltage across the resistor plus the voltage across the capacitor. So now voltage across the capacitor, which is the VC, we know. So let us substitute that. We have Vs is equal to VR plus, instead of writing this now, I write this. That is Vs minus Vse into minus T all over Rc. That is, I substituted this here now. Okay, so what do? We just make VR the subject. If we do that, we are going to transfer this to the left hand side. So we have Vs, this one is here, this is coming, minus minus Vs. This is current plus Vs exponential minus T all over Rc. See? And this is going to give us VR. So, if you look very well, you will see that we are almost done with this. What do we achieve? What we'll achieve is that from here now, it is possible for us to just see this is going to vanish. These two will vanish. So voltage across resistor is V voltage source multiplied by E raised to power minus T all over Rc. This is a beautiful equation. This is a beautiful equation. So what can we deduce from here? What can we deduce from here? Since we know that V voltage across resistor is current multiplied by R, okay? So we can say current multiplied by R is equal to Vs, and then we find the current at any instant in time, okay? So I will leave you to work on that one by yourself. Then maybe later we solve it together. Thank you. Now, we are back. I know you have brainstormed on this. So what is the current across the resistor or the capacitor? What's the equation? Okay, I know some of you would have done very well. So what you need to have done is just to remember that if we at that instant and the instant where time is equal to 0, that is before the switch is turned on. If time is 0, what is going to happen to this equation? If time is 0, the voltage across the resistor will be equal to Vs E raised to the power minus 0 over Rc. If anything divided by 0, 0 divided by anything is still 0. So VR is Vs E raised to the power minus 0. And this is the same thing as saying VR is Vs multiplied by 1 all over E raised to the power 0. And from indices, anything raised to the power 0 is 1. So 1 divided 1 times is VR is equal to Vs. Okay? And if that is the case, you know IR is equal to Vs. This I is not ordinary I. What is that? I naught R. Okay? That is maximum the maximum current, the peak current. That at that instance we have the peak current. So we can still maintain this Vs as maximum current multiplied by R, because that I is not just an ordinary I. So having known this, what do we do? Let us go into the derivation. If we understand the principle here, that VR, the voltage across the resistor, is the same thing as saying Vs E raised to the power minus T all over Rc. Okay? But this VR is the same thing as saying IR. Okay? And this IR can be IR across the resistor multiplied by the main resistor here in the circuit. Vs E raised to the power minus T all over Rc. Okay? Remember that the same current is flowing across this and that. So IR is the same thing as saying Vs all over R E raised to the power minus T all over Rc. Just like we proved here, if I divide this by R, I will have I naught. So that instantaneous current across the resistor I of R is the same thing as I of C, because the same current is flowing there in series, and that will give I naught e raised to power minus t over RC. Okay, so this is the equation for the current. This is the equation for the current. By the time we come back for break, we are going to derive for the equation dealing with charges, and then the equations dealing with the charge. We use the voltage, we use the charge, and then finally the current we have shown on the board. Thank you. Go for a short break. Coming back. Okay. To derive this in terms of charge, let us clean this board. Let us clean the board and write or redraw these circuits. It's a simple circuit. If we include the inductor or other component, it will have a differential equations of not just order one. You now have differential equations of second order and so on. Okay, so now we want to derive this equation in terms of charge. In terms of charge. So that will come to the board again. So let us take this as our voltage source. This is the key. This is our resistor connected to a capacitor. And this is our. I can decide to use this voltage source or the EMF so that it will be much easier for us to understand. Okay, this is our R, this is our C, this is our T. So now the same thing happens here. The total electromotive force here is the same thing as the voltage across the resistor plus the voltage across the capacitor. Okay, so now we are going to define in terms of charge. So this E minus Vc is the same thing as VR. We are through with this. Okay, and then we also have established that I, if we divide, this is going to be E minus Vc equal to I R. Is this obvious? Yes. So we make I the subject of formula. So we have E minus Vc all over R is equal to I. Okay. So here we begin to play with this equation. What do we have here? This is I. What is I? dq dt. So we can still substitute epsilon minus Vc all over R is equal to what? dq dt. Okay. Now, what is voltage across the capacitor? Voltage across the capacitor is normally given as Q all over C. So if we substitute that, we have this minus Q all over C, then all over this R, and that is equal to dq dt. Now, this differential equation, let us simplify this left hand side so that we can be in the same program with what we intend to do. What is this? What we do? Normal simplification. We have E. We'll get a better marker. We have E all over R minus Q all over RC. Okay, and that is equal to dq dt. I hope you don't have problem with that simplification. So we can still simplify further. RC, what's the LCM? RC. If RC come here, you have CE minus this is going to be Q equal to dq dt. Now that we have this differential equation, we can just simplify the left hand side by having negative 1 all over RC into Q minus CE, and this is equal to the Q dt, changing the charges, the amount of charges with time. So now that we have this, we can deploy our normal separation of variable. If we do that, separation of variable, we have negative dt over RC is equal to dq over q minus CE. Okay, so from there we integrate. So if we integrate, we have negative 1 over RC integral dt equal to integrating 1 over q minus CE dq. And because we're not dealing with the indefinite integral, we take the limit from 0 to t and from 0 to a certain q. Okay? So now, if we do this integration, this will be the same thing as t all over RC. And even if you take the limit, 0 to still land you here, equal to this will be ln q minus CE minus ln this is 0 minus CE. Okay, so now what we do, we recall this over RC will now be, take the log of logarithm like we did before. You give me ln q minus CE, this is charge, all over negative CE. Okay, and from here we take exponent of both sides, take exponents. So if we take exponents, we have exponential minus t all over RC equal to exponential ln q minus CE all over negative CE. So now this will vanish and we'll be left with what? We'll be left with this few thing. We'll be left with what? E raised to the power minus t all over RC is equal to q minus CE all over minus CE. Okay? So now, what do? We cross multiply. So 1 minus CE e to minus t all over RC equal to q minus CE. And what do we do with this? We collect like them. So we can add both sides. C. So we have CE minus CE exponent. This is CE exponent negative t over RC. I've just written this. I'm taking it that is equal to q. So now we've got to the function we're talking about. The function, the charge as a function of time is the same thing as saying CE into 1 minus exponential negative t over RC. This is the equation we're looking for. This is the equation we're looking for. Thank you very much.